Hi, thanks everyone. So I'll be speaking today about headless testing against real web browsers using XVFB. So if you're not familiar with what XVFB is, just bear with me. I'm going to share some background on why this was relevant to my team and maybe relevant to yours as well. We'll transition into an explanation of what exactly is XVFB, and then I'll finish off with a demo. Also, quick footnote, this is my first time speaking at a conference, so bear with me there too. Hopefully you're not about to watch my, hopefully you're not about to watch my career and professional stature crash and burn. So again, my name is Mike Ball. I'm MDB on GitHub and Clap Excitement on Twitter, and I work for a little company called Comcast. My team at Comcast is responsible for building some TV and video streaming applications. Effectively, we turn your web browser into a TV. It's 2015, and TV is not just for your set-top box anymore. So we do that with Heart in Philadelphia, as is evidenced by our Xfinity origin label response header, which we serve back with every HTTP response served by our application. And I mention this because I know historically Comcast is a company that hasn't always enjoyed the best reputation customer service-wise and user experience-wise. And my team is really working to change that. We do what we do with heart and with quality in mind, and that in turn relates to a lot of what I plan to speak about here today. So a little bit of prologue. Why am I talking about this here today? So let me lead up to that with some background on my beliefs about software development. So automated testing. I'm a huge advocate of automated testing, and I'm sure many of you guys are as well. I rely pretty heavily on automated tests within my own team to operate as an insurance policy, guaranteeing that our software continues working as it should with every change that's introduced. This helps my team move fast. It helps us understand how a changing business requirements or changing user experience impacts a larger system, and this insurance policy is in place, again, with the goal of guaranteeing customer quality and serving as kind of a digital audit trail that when something needs to change, because change is inevitable, that suite of test, or maybe in this case test failures, highlights immediately what else throughout the software needs to change to align with the evolving business requirements. And that leads into another important aspect of my philosophy as a software developer. I believe pretty strongly in continuous integration, and my team relies really heavily on a healthy continuous integration pipeline. I think in its ideal form, continuous integration ensures that code-based health is continuously monitored with each change, with each push a developer on the team makes, and that happens many times throughout the day. In its ideal form, this CI pipeline should be scientific, it should be consistent, it needs to be easily repeatable, and it also needs to be as fast and cheap as possible, but still just as sophisticated as is necessary to serve as this quality insurance policy. And I mention that because I think that's kind of true of all engineered systems, that you want them to be just complex enough to honor their responsibilities, but when they grow in complexity beyond what's necessary, that's kind of a sticky space in which, in my experience, problems occur. And conversely, when they're not complex enough to serve their need, that's a sticky space as well. And that threshold is ever changing. So we're constantly monitoring that. constantly tweaking the process to make sure quality is guaranteed. And so that brings me to my last point about a good CI system, which is that the feedback cycle should be fast. We work fast, business changes fast, the customers expect fast, so we really need to rely on speed. We need to get feedback as soon as possible about problem scenarios. So moving on with that point, I'll say I think the story of computers is kind of that they're getting cheaper and cheaper. And servers, disposable infrastructure is more and more readily available. Technology like virtualization, container technology like Docker, cloud infrastructure, all of this works in concert to illustrate this point I have, that servers are cheaper and cheaper and more readily available, and our own continuous integration pipeline relies on this pretty heavily. We rely on virtualized, disposable Linux VMs. And then within this world, especially at the JavaScript layer, headless testing is pretty important. And so historically, tools like Phantom.js, Emp.js, Rhino, Ruby Racer have all provided a headless JavaScript runtime. And this allows us, of course, to execute our JavaScript code and assert that all within it continues to work as it should, that the overall health of the software is as it should be, or that it isn't as it should be, and accordingly we're alerted to this problem. But there is a problem now. All those tools are great, and my own team relies pretty heavily on Phantom.js as a great tool and seems to have risen as the leader amongst these headless runtimes in recent years. And so this is not at all a diss on Phantom.js. I'm blown away by how great it is. But one problem remains, and even Ray touched upon this in mentioning the need to run headless IE in the presentation before mine. So what if your technology can't run on one of these headless runtimes? What if Phantom.js doesn't suffice in serving your needs? So what do I mean by this? Well, here's a few examples. Flash, NW.js, which was until recently known as Node WebKit, and Google Polymer Web Component Tester provide some examples here. So these are all three examples of some technology that Comcast and across various teams or different layers of the ginormous software ecosystem that Comcast is responsible for leverages. So Flash, of course, requires and assumes the presence of a GUI. NW.js, if you're not familiar, is a great technology for authoring distributed desktop applications across Windows, Linux, Mac OS, using web technologies and Node.js. And it too, by nature, reasonably of being a technology for authoring desktop applications, assumes the presence of a GUI. And Google Polymer Web Component Tester being the Polymer community testing tool of choice, also assumes the presence of a web component, or excuse me, the presence of an actual GUI, an actual web browser. So for the purpose of this presentation, let's focus on Google Polymer as a case study. Now, if you're not familiar with Google Polymer, I'm not going to go into too much depth at this stage, partially because my colleague, Chris Lorenzo, you want to raise your hand, Chris, is going to be giving a great introduction to Google Polymer this evening at 5:45. Is that correct? So be sure to check that out. But the basic skim the surface background, as is relevant to my talk here, is that Google Polymer is some great technology used to author HTML web components. This is a technology that various teams throughout Comcast have taken increasing interest in as of late. And like I mentioned, this tool, Web Component Tester, is the Polymer community testing tool of choice for automating Google Polymer tests. But here's the deal. Web Component Tester, like I mentioned previously, assumes a GUI. And so these virtualized CI build agents I mentioned earlier, they don't have a screen. They don't have a GUI. They're cheap, disposable VMs. And so in this case, Web Component Tester really challenges some mental infrastructure assumptions. And so the problem isn't mountable. There are some candidate solutions provided by Travis CI, for example, or Sauce Labs. Travis CI has some really extensive and great documentation on how to run GUI headless browsers on its own infrastructure. And incidentally, their technique also leverages XVFB, which I'll cover in more detail here, and a headless Firefox. So that's great. And Sauce Labs, if you're not familiar, is also a great option. Sauce Labs offers a Selenium cloud with access to over 100 device OS browser combos. So that's a great option as well. But what if your team can't use these tools? So why might your team not be able to use these tools? Well, budget might get in the way. These are vendor services, and your team might just not have the capital to pay for it. Complex software licensing agreements may not meet your needs for various reasons. Or maybe the amount of load that your team will generate is just prohibitive. So what do we do in these cases? Well, that's really where my ideas for X Virtual Frame Buffer come into play. So X Virtual Frame Buffer, more commonly known as XVFB, I'm kind of using the two interchangeably in this presentation, it's not new technology, and it's not JavaScript technology, but it is some technology that allows you to run GUI applications like web browsers with no GUI, so with no screen. So let's talk a little bit about XVFB, and I'll hopefully provide some contextual understanding for what it is before I lead into my demo. And with that, quick sidebar, let's talk about the X Windows system. So the X Windows system is how GUI displays are rendered on Unix-like systems. Unix-like systems being Linux and Mac OS. And the X11 Display Server is the current release of the X Windows system. So again, this is a windowing system for bitmap displays used to render GUIs. And this is effectively how visual elements are rendered on a screen and available for user interaction via mouse click or visual GUIs with qualities like color and shape on Mac OS and Linux. And so with that, what is X Virtual Frame Buffer? So X Virtual Frame Buffer, or XVFB, behaves just like any other X server, the difference being no graphical output is rendered. So it allows us to perform all graphical operations in memory without showing screen output. So again, it doesn't require the computer running it to have a screen, as is the case in my own team's continuous integration workflow, and I'm sure that's true of many other teams' continuous integration workflows. We're relying on VMs, either in the cloud or even managed VMs that have no display. They have no screen. So that brings me to the question. So with all of these problems in mind, and bearing into consideration XVFB as some candidate solution technology, I doctored up a Polymer testing box. So this is a repo available on my GitHub. Follow along. My GitHub username is MDB, and the testing box is polymer-testing-box. And so a little disclaimer, I'm not advocating necessarily that this is the best or most appropriate way to solve this problem for your team. This is just a reference implementation, proof of concept for how you can run your automated tests in a headless VM. So the core technologies I'm going to be using throughout the presentation and demoing Polymer Testing Box are, of course, XVFB. We're going to use Ansible. Ansible is a configuration management and provisioning technology comparable to Chef or Puppet or CF Engine, typically used by system administrators and operations professionals in provisioning servers. We're going to install Google Chrome, we're going to install Firefox, Node.js, Bower, and Web Component Tester, which are all the prerequisites for running Google Polymer Web Component Tester tests. Okay, so demo time. So again, here's what we're going to do. We'll provision a Vagrant Ubuntu box. Ansible is then going to do its work installing and configuring all necessary dependencies. And then we're going to run some Web Component Tester tests against Polymer Web Component. So quick sidebar on Vagrant. Disclaimer, for those of you who aren't familiar with Vagrant, this is not JavaScript, but it takes a village. So I feel obligated to say that at a JavaScript conference, right? But this is some great technology that helps serve our needs within the JavaScript community. So Vagrant is built on VirtualBox, and it's effectively a tool to spin up lightweight headless VMs. But a quick point I want to make about this is that in this case, on my laptop, Vagrant is the provider of this Linux VM, but that provider could just as easily be a remote or cloud provider, such as Amazon Web Services or DigitalOcean or OpenStack. In this case, for this demo's purposes, I'm just using Vagrant, but in theory, this Ansible playbook, playbook being the Ansible metaphor for how provisioning happens, could take effect on a box provided by a different provider, like a cloud provider. And so the primary way that we communicate that we want an Ubuntu VM from Vagrant is via this Vagrantfile. So again, this is also not JavaScript. This is Ruby, but I do want to point out a few things here. There's more going on, but in the larger Vagrant file, which you can see in my repo. But quick points here. So number one, note that we're forwarding port 5900 to 5901 on the host machine. So the host machine in this context being my MacBook. So the VM becomes available to us on my MacBook via port 5901. And then secondly, we're declaring, hey Vagrant, provision this Ubuntu box we're asking for via Ansible. And the instructions for how to do so are contained in this playbook.yml file. All right, so the Ansible playbook.yml file, again, not JavaScript. Ansible is Python. But again, I hope you see the relevancy. We're going to, as per directive of this playbook.yml file, install and run XVFB on display port 0. We're going to install Node, Bower, Web Component Tester, and then we're going to install Chrome and Firefox. So we kick all of this off by executing, by running Vagrant up. So that gives us the base Ubuntu box and then kicks off the Ansible provisioning process. Point here is that this is, I'm storing my infrastructure in code here. So this is an easily repeatable scientific process. This is not a fragile managed server. This code allows us to repeat this process again and again and again and get the, in theory, exact same VM again and again and again. So when that's all done, we're going to shell into the Polymer testing box, which I'll do via Vagrant SSH. And then I'm going to clone a Google Polymer web component. So in this case, we'll clone Core Ajax, which is a Google Polymer component maintained by the Polymer team that provides some Ajax functionality within Polymer. So we'll clone that. I'm going to check out version 0.56 of Core Ajax. I'll do that because I want to demo working tests, and I know 0.56 is an official release, so its tests pass. And then we're going to run bower install to install the Core Ajax dependency. So again, this is all happening on the Polymer testing box, Vagrant box. Okay, so now I'll demo running Web Component Tester. So what you'll see is I'll run WCT, which is the Web Component Tester executable, setting the environment variable to DisplayPort 0. So I'm telling Web Component Tester to run on DisplayPort 0. And remember, per our Ansible playbook, X virtual frame buffer is also running on DisplayPort 0. And we'll see evidence, I'll go ahead and kick this off, that Selenium is going to spin up both Chrome and Firefox. So we see Chrome 43 and Firefox 38, which were installed via Ansible. And we're going to run the Web Component Tester tests in each browser. So you can see we've passed all of our tests in each browser, and that happened with no screen output. That happened entirely on my Vagrant box. So that's the core of what I seek to demo here. Thanks. I can understand any skepticism you have. How do we know that Chrome and Firefox really ran? And what about debugging? What if you actually need to poke around in development or maybe even remotely to figure out why are things failing? You might need a GUI to do so. You might need to actually connect with a web browser. So I have a solution, VNC. While the Polymer testing box has no screen, it has no GUI, your Mac does. So what this means is that we can open a VNC connection from, in this case, my MacBook to the Vagrant box. And because my MacBook has a GUI, it has screen, the draw commands and all of the GUI commands executed will have a screen to take effect on. So step one on the Polymer testing box, we'll have to install a VNC server. So I'll do that via sudo apt-get install X11 VNC, and also run this on DisplayPort 0. And then on your Mac, or on my Mac rather, I've brew installed Tiger VNC Viewer. Any VNC client will do. And I'm running this on localhost 5901. You'll recall that I forwarded port 5900 of the Vagrant VM to port 5901 on my Mac. Sorry for it's a little small. I wasn't sure what kind of screen real estate I have to deal with. But on the left, you'll see this is my VNC connection opened from my Mac to the Vagrant box on the right. So I'll go ahead and run the same command I ran previously on the Vagrant box, and now on the left, it's going to be a little squished up, but hopefully you'll take my word for it that you'll see Chrome and Firefox actually open and execute these passing tests. So there was Chrome first, and there's Firefox, and all tests pass, and then the browsers will close. So again, that code is available at my GitHub profile, MDB Polymer Testing Box. And quick extra credit, I also doctored up a solution for running in NW, running and testing, both unit testing and end-to-end testing, an NW desktop application on a similar box. So as for next steps, I'm hoping that you could see how you could kind of adopt maybe some of what I've proof of concepted here to spin up some cloud infrastructure or something during your own builds, maybe leveraging AWS, DigitalOcean, or OpenStack, or some comparable cloud provider. I also have a harebrained idea for how similar VM could be spun up and provisioned for building and unit testing ActionScript. I think this also opens a lot of opportunities for some advanced web scraping for those wacky websites which just don't seem to behave at all in Phantom.js for whatever reason. And it also provides a path towards headless functional testing if that's something that you're interested in. So that's it. Thank you very much. Again, I'm Clap Excitement on Twitter and MDB on GitHub.